Today I'm going to try to explain the twins paradox from special relativity and show how it's not really a paradox. Now, if you haven't heard of this famous thought experiment, it goes something like this. A twin gets into a rocket ship and flies off to a distant star at a significant fraction of the speed of light. And when he comes home, he discovers that while he's only aged a few months, his twin who stayed on Earth is many years older. This doesn't look like a paradox at first. After all, one of the predictions of special relativity is that as objects move faster, time slows down in their reference frame. So the fellow who gets into a very fast rocket ship is going to have time slow very slowly compared to his twin brother who remains at Earth. But the paradox appears when you remember the relativity part of relativity. Motion is relative. What that means is that we can just as easily say that the fellow in the rocket ship is at rest, while the Earth and the rest of the galaxy is zipping by him at a relativistic speed. And that in turn means that from the perspective of the twin in the rocket ship, time is slowing down for the twin on Earth. And yet somehow, it's still the twin on Earth who ages. So why the asymmetry? Now, most explanations of the twin paradox point to the fact that the twin in the rocket ship must undergo acceleration. And that's why there's a difference. While this is true, and there are some very good animations on the internet that illustrate how acceleration resolves the problem, it's worth noting that the twin paradox is a problem in the special theory of relativity, which only deals with uniform motion and inertial reference frames. And Einstein didn't even address the question of acceleration until he published the general theory of relativity. So I'm going to try to illustrate why the twins paradox is not actually a paradox without referring to acceleration at all. Now, I have here two model rocket ships, carefully handcrafted from Lego to be the same length and distinguishable by their color. Now we're going to assume these ships are traveling in opposite directions at 95% of the speed of light relative to each other. There's no acceleration here. They're just zooming along from the very beginning of the experiment to the end. And it's all perfectly symmetrical. We don't know or care which one is really at rest. In fact, let's assume they're both moving with equal and opposite vectors, and we're right here in the middle watching them go by. Here's what we see as they pass each other. First, the noses of the ships are lined up. We'll call this event A. Then, as the ships continue to move past each other, there will be a moment when the nose of the white ship is lined up with the tail of the red ship. I call this the blue ship in my script because I wasn't looking at the models that I had made, but it's actually more red than blue. Now, you'll notice that event B, when the nose of the white ship meets the tail of the blue ship, in this frame of reference, happens at the same time, because they're the same length, as event C, which is when the nose of the blue ship reaches the tail of the white ship. That's event C. Event A, event B. Event A, B, C, and D. That's when the tails are lined up. We'll call that D. Now, a very important thing to understand about special relativity is that space and time are both affected by high speeds. So not only does time appear to slow down for rapidly moving reference frames, but they also appear to contract in the direction of travel. It's not a linear formula, and so the two ships moving past us at 45% of the speed of light still appear to be close to their same rest lengths. But if you're traveling along at 95% of the speed of light, you'll actually contract to approximately 1/3 of your rest length, like this. So, let's look at the passage of the two ships from the perspective of the white ship. Now, from the white ship's perspective, it's at rest, and it is the red ship that is passing. And the red ship is contracted to 1/3 of its length. We see first event A, when the noses pass each other. Then, the next event is when the nose of the white ship passes the tail of the red ship. Now, you'll notice that since the ships are in very different lengths, they don't happen. This one happens fairly quickly afterwards. Finally, we get, well, not finally, but next we get event C, which is when the nose of the red ship hits the tail of the white ship, and then finally event D. The same sort of thing happens from the perspective of the blue ship, except that now it's the white ship that is contracted in length. So we see event A, followed by event C, and then we get event B, and finally D. So notice this. The events happen in a different order in the different reference frames. A, B, C, D in the white ship's frame, and A, C, B, D for the blue ship. the red ship. When the white ship experiences event B, event C has not happened yet. And when the blue ship experiences event C, event B has not happened yet. It's also worth pointing out that the total elapsed time from A to D is the same in both frames. And in fact, the time from A to B to C in the white ship's frame is equal to the time from A to C to B for the blue ship. But the time from A to B is not the same in both reference frames. And likewise, the time from A to C is not the same in both reference frames. Now, let's apply this to our twin paradox. Say that instead of the blue ship being a ship, it represents the distance between Earth and some distant star. And that the twin is traveling in a rocket ship which is at the very tip of the white ship. Again, from a point at half the speed between the two, we see them pass like this. A, B, C, D. B and C happening simultaneously. But what do we see from the perspective of the white ship? The white ship leaves Earth at this point, because this is Earth, and this is where the astronaut is sitting. We go to event A, B, and we're done. C happens a long time after we've gone well past our destination, and then D happens even further after that. So we stop at event B. That's when we're done, as far as the white ship is concerned. Quite different from the perspective of the red ship. We start with event A, then we go to event C, which happens in this frame about the same amount of time afterwards as event B happens in the other frame. We go A, C, then a whole lot of time passes, and we get to event B, and then D. So, notice that because of the way we've defined the events, the trip ends at event B. How much time has passed in each reference frame? Well, from the perspective of the white ship, the sequence is A, B, C, D, so the trip stops at the second event, and we don't need to wait for event C to happen. But from the perspective of the red ship, Earth's reference frame, we first had to experience event C before we could get to event B. Event C happened for the Earth as soon as event B did for this white ship, but then there was all this extra time to wait around for event B, which is why the twin at home ages more than the one on the ship. If we defined the trip in another way, say by telling the astronaut to keep flying until it looked to him that the Earth was a full ship length behind him, then the aging would be opposite. It would look like this. You go through event A, B, and then he'd keep going until C. Oh, there, now Earth looks like there's a full length of my ship behind me. Of course, he's gone well past the destination in the first example, but it's taken more time for him. And so he would age more than if it were observed from the point of view of Earth, where we see event A, then event C. Oh, look, that happened almost immediately. We don't even have to wait around for event B. So you see, the two situations are actually symmetrical, and we don't need to worry about who's accelerating in order to explain why one twin ages and the other doesn't. What we really need to look at is the definition of what constitutes the endpoint of the trip. Now, it's pretty artificial to say, fly until it looks in your reference frame to Earth for Earth to be 4 light years behind you, but that's not the point. The point is that reference frames change in special relativity. And that means that the time that elapses in one frame isn't necessarily going to be the same time that elapses in another. And it also means that events happen in a different sequence. And it's that different sequence that explains the asymmetry. I hope that's been helpful. If you have any questions, feel free to post them in the comment section. Thanks for watching.